Okay. Hello, everyone. This is Tianle Wang from Brookhaven National Lab, and today I'm going to present our recent work of the integration of Globus Compute and Panda Harvester and its application in the Atlas workflow. So this is supported by the this work is supported by the HPC project, and we have a large collaboration between a huge number of national labs, and I would also say special thanks to the Globus Compute team, which that gave us a special, very heavy assistance in making this work possible. Okay, so firstly, I will talk a little bit about the motivation. So basically speaking, we face great data volume exploding in the high energy physics workflow. For example, in the high luminosity LHC and the DOOM workflow, we estimate there will be an order of 10 to 100 data volume increase over the next 2 decades. So we want to find some solution beyond the HPC because, for example, the traditional grid and panda system reaching the throughput limits, and also we have a very extensive use of machine learning models which requires GPU for better performance. And because of that, we will need a leadership class HPC cluster, for example, Permada, Polaris, Frontier, Aurora, etc. And one of the main focus of the HPC project is to look at this performance portability. So we want to look at first, for example, the task level porting, for example, porting from CPU to GPU, different programming model, etc. And the second thing, which is the focus of this work, is the workflow infrastructure porting part. So we'll be using the Atlas workflow as a test use case. Okay, so I will give a very short introduction to the Panda and Harvester. So basically speaking, you just need to know that the Panda and Harvester serves as a resource provision and workflow management system. So currently, when we are trying to run jobs on HPC, all the Harvester instances are deployed locally on the HPC, and we will have, for example, one or more local Harvester instance per HPC site. So our main focus is trying to use a centralized Harvester, for example, as CERM, and use some remote submitter plugins that comply with the DOE HPC site policies. So that's the reason that we want to look for example, the Globus Compute backend. So in this plot, we just plot what the integration will just looks like, and the most important part is inside this purple dash box. So we want to have a centralized harvester which spans multiple submitter, monitor, and sweeper. And those are the 3 most important plugins in this integration. And the submitter is going to remotely submit the job, and the monitor is going to monitor the job status, and the sweeper is focusing on the clean up the workspace and the job killing part. And and on the rest of this talk, I'm just going to talk about these 4 key components: the submitter, monitor, sweeper, and the endpoint configuration. So for the submitter, our main goal is to have a remote jobs is to support remote job submission and the metadata matching between the Harvester and the Globus Compute. So there is a huge debate on how are we going to design this sort of mapping between the layer in the Harvester and the layer in the Globus Compute. So basically speaking, we have the two favorable options that we have is the one that is to have a single Panda pilot per parcel worker, and second is to have a single harvester worker, which includes multiple Panda pilots per parcel worker. And currently, we decide to stick to the second design option because it's more consistent with the local submitter plugin. And with this design option, our the mapping becomes, for example, we will have multiple pilots that are wrapped within a single bash function, and this will be mapped into a harvester worker, and then maps to a parcel worker, and then we will have a single parcel worker per sandbox job. So currently we will try to with this kind of design, we are trying to support 3 levels of parallelism. We want to have multiple pilots per node, multiple nodes per job, and we will have multiple jobs running in parallel. So there is one issue that we saw in this integration, that is the latter 2 parallelism are sort of inconsistent inconsistent with each other. So our current solution is to choose a simple runner and make sure the parcel worker just on the first node, and then set the parallelism to be bigger than 1. And that will help us to reach the 3 level of parallelism perfectly. And the second plugin is the monitor plugin, and its goal is to monitor the status of the harvester worker. It doesn't need to monitor the status of the pilot because the Panda pilot is by itself has the monitoring service within it. So currently, the biggest issue with earlier the biggest issue with the monitor is that for the local monitor, they can start working focusing on the sandbox since the querying status of the sandbox. For example, we can monitor the sandbox since we run the sbatch command. However, with Globus compute, we don't know the sandbox ID until the Globus compute task starts executing. So basically speaking, we need to first have the resource provision finished, and only after that can we know, for example, for a Globus compute task, which sandbox it is actually being executed on. And more severely, sometimes Globus compute does not return a clear error status. For example, if the jobs sort of if the sandbox reached the time limit, then sometimes Globus compute will not give us a very good sort of error message telling us what is actually happening. So our current solution is to do the 2-stage monitoring. In the first stage, we're monitoring the Globus compute task until it actually gets executed. So currently, one issue with that is the Globus compute actually cannot tell us whether a task is actually being running or is waiting for the resource provision to be finished. So we need to introduce we actually introduce a method to work around that. And in the second stage, we want to do the remote querying. After we make sure that the Globus compute task starts executing, because it's the mapping between the Globus compute task and the sandbox job is one-to-one mapping. We can just remotely query the scheduling system using Globus compute endpoint that is running on the edge node. So because of our mapping, because the monitoring happens for every 30 to 150 seconds, and because of the mapping that we choose, actually it gives us a very good throughput and latency, and the internet traffic won't be the bottleneck in the monitoring plugin. Of course, it has some granularity issue, but this is not something that we are mostly worried about at this point. Okay, and the next plugin is a sweeper, and the sweeper is trying to handle 2 things. The first is the workspace cleanup, which is simple, and second is to kill the harvester worker. So this one currently has some issue with that, and the most important thing is that once the Globus compute task is still in the queue, we don't have a method to kill this task. So the last thing is the configuration for the endpoint. So currently we are using the multi-user endpoint with a single user, because currently we're testing on the permatter, and we use for example, collaboration account to support that. And for other facility, we will need a multi-user capability. And currently we can have the local submission successful, and it scales up to 4 nodes and 5 Slurm jobs running in parallel, and can running stable for more than 2 weeks. And currently we're working on the remote submission, and the first try is successful at this point. And in our future plan, we are trying to run that on other HPC cluster like Polaris or other machine without outbound connection, and we want to move the harvester to Slurm, and also look at other high-energy physics workflow like Doom and some other like NCMS, for example. Okay, so that's everything. That's my talk, and thank you so much.